So, we will continue with our discussion on sampling. So, last class we talked about sampling and the objectives of sampling, different objectives that we can think of. So, one of the things we had discussed is in terms of location is the sampling objectives. We need sampling objectives, and these objectives, based on objectives we can do a sample location. Where do you want to sample? What do you want to sample? Okay. Right. Okay. So, the next question that you will have, and there also a number of samples and all that. So, number of samples. So, what is the definition of a sample? So, we discussed that definition of a sample is a quantity, it's amount. So, what is our goal of sampling? So, our goal of sampling is eventually we would like to get some measure of concentration. This is our goal, concentration. The concentration means concentration is mass by volume or mass. It is a mass fraction or a mass concentration. So, it is either we are talking about rho A1, we are talking about rho A2, or we are talking about WA3. These are the things that we are interested in measuring eventually. So, you are interested in getting mass over some volume of air, and this is mass over some volume of water, and this is mass over some volume of solid. Yeah. So, if we want to get this is the information we want, we need this and this. Yeah. So, this brings us this denominator here is what we would call as the sampling volume, the sample volume. We will come back to this in a minute after this discussion. We will come back to number of samples a little later because it relates to something else. Sample volume, yeah. Let me take an example of one of the analysis methods. So, I will give you an example of one of the analysis methods before we go on with this. So, what we mean by sample volume, okay. What is the analytical instrument you are all familiar with? You can just name some and I will pick what is the most commonly known analytical instrument. So, example of an analytical instrument. Huh? GC. How many of you know what a GC is here? Please raise your hands. Okay. Next. HPLC. How many of you know what an HPLC is? Okay. Less than half. How many? Anything more? You have, from high school you have done a lot of analytical instruments. UV. What UV? UV spectrometer. How many of you know what a UV spectrometer is? More number of people, but not all. Okay. Huh? Turbidity meter. How many of you have seen a turbidity meter? 6 people. Next. Anything? Start from high school. Start from high school. Huh? FTIR. How many of you have heard of FTIR? 6 people. Anything you have used from high school? What is the pH meter? Okay. Then something more. Huh? Burette and pipette is not an analytical instrument. It's a handling. Microscope. Okay. Weighing balance. How many of you have used the weighing balance? How many of you have used the weighing balance? Please honestly raise your hands. Then if you don't raise your hands, we will ask you to go back. All of you have used weighing balance, hopefully, somewhere. Weighing balance. So, we will start with weighing balance. Okay. It measures mass, weighing balance measures mass. Okay. Now, let us say that we will do a simple measurement of total suspended solids. So, I will describe you what the total suspended solid method is, and then based on this example I will explain what we mean by what we are trying to discuss here. Okay. So, we will go to the next page. We will do total suspended solids in water. So, what we are measuring really is rho 32. We are measuring solids in water, we are not measuring chemical concentration, we are measuring solids concentration in water. So, it is like this, you take a water sample, the water sample looks muddy, okay. It looks muddy, then you know that something is there in the water sample. Yeah. So, in order to measure the amount of this thing, so what we are measuring is M3 by volume of 2, this is our measurement. So, we would like to measure the solids that are suspended in this water sample. Yeah. So, what is the simplest way to do this? You simply want to measure mass over volume. So, what are two measurements we need? One is the volume of this water. So, I can take a water sample, I can measure, if this says 1 liter, let us say 1 liter, I can fill up this water to 1 liter and I know that this is 1 liter, I know the volume, right. Let us assume that we know it is 1 liter, okay. And then how do I measure the mass that is contained in this 1 liter? This is suspended, which means that if you take a snapshot of this, it will look like this, it will look like this. The mass is all suspended in the water. So, what do I need to do in order to measure the solids, suspended solids? Yeah, I need to filter. What am I doing when I am filtering? So, I am separating the separation of the solids from the water. I am separating solid from water. I can do it in different ways. Okay. The simplest way in which it is done is by filtration. Filtration. What we do by filtration is, I take a filter, I need to trap these particles physically, I need to contain them physically using a filter, some kind of a device straining. And here I put the water, and what I get here will be clean water. So, which means that at this point when the filtration is done, what will happen is, on top of the filter I will see a thick layer of some thick layer of solids that are trapped and clean water. That is collected. So, this is what we call as a residue, and this is a filtrate. Yeah. Now, how do I measure the amount of solids here? I have separated it, and the solids that are collected on the filter paper, I have to measure it. Now, I measure it using weighing balance. I do what is called as a gravimetric measurement. When we say gravimetric measurement, it is mass measurement. Gravimetric is mass measurement. Gravimetric measurement is mass measurement. We use a balance, weighing balance to do it. So, here what we do is there is a filter paper, that is on the thing. So, the mass M3 we will write as M0 is mass of an empty filter paper. So, this is the empty filter paper. Before we start the filtration, the filter paper has a weight, it is empty filter paper, and once we finish, so this is the loaded filter paper. So, MF1 minus MF0 should give you M3, that is there, divided by the volume of water, will give you the total suspended solid. This is a simple, very simple assessment of it. Now, how is this related to sample volume? Because there is a certain amount of suspended solids concentration in the water. If I take a water sample that does not look brown, does not look even yellow, can I say that there are no suspended solids in it by this method? I mean, I cannot say it unless I do this method. Okay. So, if I know that if I take 1 liter of water, okay, what is the condition under which I can make this measurement using this method I have described? There is a condition, there is an assumption or a condition under which this will work. Is it possible that I get a value of total suspended solids as 0? Yeah? When? No, when, based on experiment, when? Pure water and all, you do not know it's pure. When? So, when TSS is 0, when MF1 is the same as MF0. But when this happens, can I absolutely be sure, can I say with 100% certainty that there is no solids in the water? Why? Huh? No, we are not talking about it, we are only talking about suspended solids.
There can be particles which are smaller than the diameter of the filter.
That is one. One possibility is that the filter is not trapped all the particles, that it has gone through. Let us relax that assumption. Let us say filter is the best filter you can get for all particles that you can think of, and it will stop that. But that is the one of the points. What other reason can there be when you get a 0 reading, but you are not really sure that it's actually TSS is 0? I mean, what? Let us assume that is all not true, no errors in measurement, the filter is nice. What do you know about balances? This has to do with balance, the weighing balance. The question that we are posing is, if MF0 is the same as MF1, are you sure that TSS is 0? With MF0 and MF1 being equal, which means there is no change in weight that is registered. That is the true statement. Yeah. What does that mean? I am giving you another example. You look here. Are you seeing? You see this room. You are able to see the screen here. Do you see anything in between? No. Does it mean there is nothing in between? How do you know there is something in between? Are there any particles in between in air? How do you know? Can you see it now? You can't see it, you can't prove it. But how do you know it is there? So, what is the meaning of that? You cannot detect it with whatever you are doing right now, but you can detect it with another method. So, what this means is that it is This is not 0, it is below detection limit. This is the accurate term for analysis, chemical analysis, any analysis. You are not allowed to use the word 0. It's a very philosophical thing sometimes, but you cannot see it, that is all. It does not mean that it is not there. It is true for a lot of measurements people make. It is true for this PM10, PM2.5 and all that. People did not know there is something called PM10, PM2.5 or nanoparticles until they had the tools to see it. Okay. So, it is the accurate statement is below detection limit. Maybe it is there, maybe it is not there, that we do not know. It is not there. So, it is below detection limit. So, coming back to this below detection limit, how many of you have what kind of balances have you used? Weighing balance. Have you used this digital balance, the 4-digit balance? This is a 4-digit balance. Yeah, this is what a filter looks when it is clean and when it is dirty. This 4-digit balance, if you look at it here, I do not know if you can see it clearly. Let me try to expand it. So, you can see something here, 0.0000 grams, it says 0.0000 grams. So, this is 0.1, the last digit is 0.1 milligrams. Yeah. On top here somewhere you will see something written. What you will see is the range of this instrument, let us say 50 grams to 0.00001 grams, 0.1 milligrams. So, if anything is there below 0.1 milligrams, you will not see it, it will register as 0. Okay. So, that is similar to what we would call as close to detection limit. It is not necessarily the detection limit. What they write there is not the detection limit. What they write there is what they are able to register. Detection limit has a bigger meaning, we will come to that in a minute. But the instrument has a range in which it can operate. Okay. If it is below that range, you cannot see it. So, what do we do in our example? If you coming back to our example, if you are not able to see a difference, what can you do to check if there is a difference? So, our TSS is M3 by V2. Yeah. Let us say for example, let us say that the detection limit for a gravimetric balance, for a weighing balance is 1 milligram, 1 milligram. This is below it, it cannot measure. The minimum it can measure is 1 milligram, right. Now, I take 1 liter of water sample with a TSS of 0.5 milligram per liter. I am not going to see anything in the balance. My balance, let me say to be very clear, I will put it as 0.3. Sometimes this 0.5 will fluctuate and show up as 1, that we do not want that, it is 0.3. I know this through some other methods, I have analyzed it, but if I put this, I filter 1 liter in a filter paper and I put the filter paper, I am going to register a weight difference MF1 minus MF0 is going to be 0.3 milligrams, because I am using 1 liter of water sample. So, in the instrument I am going to be seeing 0, instrument will say 0, it is below the detection limit of the instrument. If I want to be, if I do not have any other instrument to measure this, what can I do? What can I do? So, I can increase this volume, this 0.3. If I want to increase say 0.3 milligrams per liter multiplied by volume must be greater than the detection limit. In this case it is 1 milligram. So, I can say my volume must be greater than 1 milligram divided by 0.3 milligrams per liter. So, it is at least around 3.3 liters or something. So, I will have to use at least 4 liters in order to see something in this. So, the sample volume that you collect is related to the concentration that you expect to see in the sample and the detection limit of the instrument you have at your disposal. Is there another word? Is there another word for detection limit? Yeah? Detection limit, there is something called, this is detection limit. What is the commonly used term to represent the capability of an instrument to detect? So, what would you like in an instrument? A good instrument, you would like to have higher detection limit, lower detection limit? Lower. You must be able to go as low as possible. Yeah. So, what is that feature of an instrument called? Huh? No. No. Sensitivity. It's called sensitivity. The instrument is very sensitive, means small changes it can, the more sensitive it is, it will respond to very small changes in whatever is the stimulus you put on it. Okay. Does not matter how the instrument works. Most physical balances do not measure actual mass, they measure some pressure, and that pressure is converted to some voltage or something. All of them are like that, okay. Except the balance that you have in the old vegetable shops, they will put one weight on one standard weight on one side, the other one on the other side, they will balance, and then they will see. Even there, the sensitivity is the middle thing where it is moving, it has to be in the middle somewhere, all that is there. So, all digital balances are based on pressure transducers there, measure the pressure. So, the pressure, the more sensitive that pressure device is, the more sensitive the weight measurement can be. So, which means that it will also, we will come to that in a minute. This feature of sensitivity, when you see sensitivity, when you look at instruments listing characteristics, specifications, you will see sensitivity, and it is listed as the lowest concentration. The lowest theoretical concentration that the instrument can measure will be listed there. So, in the case of the balance 0.0001 grams, it can detect 0.00001 grams. Okay. Whether it is useful to you or not is a different question. Okay. But somebody has tested it and said this is the minimum, it can actually give you a sensitive reading, some reading. Okay. How many of you have used the digital balance for your properly for your work? Few of you have used it. Yeah. What is other thing that you observe in balance like this? When you put a sample, what do you do? What is the procedure that you follow? Huh? You make it 0, then you put your sample, and then how long does it take for you to get a reading? Many of you said you close the this thing. So, there is a door here. Okay. This is the sample. This part here, what we are talking about here is the sample plate. Okay. So, there is a door here. Why do you close the door? You have seen a lot of balances, right? Outside we have this big large in railway stations or someplace, we have a big weighing balance. People take 50 kilos of this thing and put it on it. It is not closed or anything, it is open. So, what is the reason? Why are you closing it? More sensitivity? No, sensitivity is sensitivity, right? I put a gram or piece of dust, it will also, it is supposed to weigh, it will weigh it. But what is the problem? What do you observe if you do not keep the door closed? So, this is the balance, right? This is your weighing plate. Yeah. If the door is open, what do you observe in the reading? It fluctuates. Yeah, it fluctuates. How will it fluctuate? Where will it fluctuate? Most of the times it will fluctuate in the last digit. So, it will be 0.0001, 2, 3, 4, 2, 1, 0, 2, 1, 3, 4, 1, 2, 3, 4. So, what do? You close the door, it is still fluctuating, then what do? This last digit is useless because it is fluctuating. So, if I track the signal, if I connect this say to a computer, or if I have some student who is sitting there and who has photographic memory and who keeps reading out the numbers as they are appearing, and somebody is writing them down and they are plotting it. If they plot it, the number of readings, it will keep going like this. Yeah. From this kind of reading, how can you infer anything? What will be the number that is useful to you? The average. Yeah, is that enough? Suppose I do not put, before you are going to 0, you said you will 0 the instrument, right? Yeah. You have not even put your sample. If you just let the instrument on and it is fluctuating. If you put it as 0, it will go to minus 1.12, minus 2, minus 2 plus 2, minus 2 plus 2. It will fluctuate there also. Yeah. So I put a sample, it is still fluctuating. How do I know that I have put the sample? Whether it is actually showing a signal or not. You are understanding my question? It is fluctuating, and then I put a sample, it is still fluctuating. I am unable to determine whether, let me give you a, so I have nothing on my sample, I am getting this reading. This is the kind of signal I am getting, right. Now I put my sample, yeah. Suppose I get a signal like this, reading like this. Can I make any sense out of this? Just looking at it, you know that you have put a sample, you know there is something on it. I can see something, but I am not able to see any reading. I know that it has something. What is the problem?
Maybe calibration.
We are not there yet. That is the next question. But here, what is the problem here? Can I make any sense out of this?
The delay in measurement.
No delay in measurement. It has to do with the measurement itself, the magnitude of the measurement. It is still related to detection limit only. Okay. Now, when will you consider? Suppose I have another sample which looks like this, which let me write it in green color. Is there a difference between this, the green one and the red one and the blue one? The blue and red, you cannot differentiate very clearly that this is, we are not able to find out whether if it is, what is the red, what is the red, what do you call the red? Is there a term for this red signal? When there is no sample, the instrument is fluctuating, it will give you some reading. Huh? It is not zeroing, it is, it is called as, the red part, the red is called as noise. The blue is a signal, the green is also a signal, but in the red and this two I cannot differentiate between the signal and the noise, it is very close to each other. In this case I am able to differentiate between the signal and the noise. So, the signal in the green is much significantly greater than the noise. This signal in the blue, I am not sure, is almost the same as the noise. This is where we have this term called as the signal to noise ratio. Okay, signal to noise ratio. So, what this means is that is the following. So, if you take a simple signal, if this is a noise, if there is some signal that goes well above that, I am able to verify that it is greater than. So, there is a statistical method to find this out. So, what is this? When you have signal like this, it is a distribution. You have a large distribution of signals, large number, and you have another distribution of noise. The statistical question that you ask here is, you do what is called as a hypothesis test. How many of you have done statistics? Statistical hypothesis testing. You have heard of hypothesis testing? You don't know. We will not do it in depth, but go and read about it. We will verify if this distribution signal number that you are getting is different, significantly different than the noise. So, statistically when you do this, it turns out that people consider, you can make your own choice, you can decide that if the signal and noise are this much 10% apart, I will consider it as signal, but your uncertainty is very high. People ask you, is there really a signal? You can't really say yes surely. So, your certainty about the separation of noise and signal must be really good, okay, that you are reasonably confident that this is the signal and this is not the noise. What we mean is that we are actually seeing some value of the mass and we are not just seeing noise, okay. Otherwise what will happen is you will get a wrong reading, maybe there is not, it's below detection limit, but you are assuming that it is near detection limit, you will report a higher mass or something like that, that's a problem. So, the signal to noise ratio, the general assumption, this gives you rise to a term which is called as a method detection limit. It is called as method detection limit because it is not specific to the instrument, it is specific to the way you are doing your measurement. For example, if I keep a filter paper which is empty, that is my base measurement. If I keep a filter paper which is loaded, that is also that is a signal measurement, right. The noise measurement and signal measurement, the difference between these two is what I am interested in. So, it is related to my method, the way I am doing it. It is not the instrument supposed to give me 0.1 milligrams, that is what is called as the instrument detection limit. But the instrument detection limit is useless in many cases because we are not going to go there, we are always doing something else, we are not working there. What we are now, we are not saying that it is the difference, what we are saying is the actual measurement itself, what we are saying is it is related to this noise, some fluctuation is happening, and that is a different thing than what is the lowest, what is the least count. So, the method detection limit is defined as 3, this 3 number is a statistical test statistics, it is a t test, I do not want to give you details now, it is a t test with 95% certainty or something. So, it is 3 multiplied by sigma, which is the standard deviation of what is called as a blank, which is n equals 7. What it means is, it is the standard deviation of 7 non-consecutive blank values. Blank means there is nothing, no sample is there. So, this comes to our definition of what is a blank. Okay. A blank, as the name suggests, is something, there is no analyte. The term analyte is a reserved keyword for whatever you are measuring. In this case, you are measuring the solid, that is the analyte, yeah, that is the analyte. So, the no analyte is the keyword. So, a blank is something which does not have the analyte. There are different kinds of blanks, we will talk about that in a minute. So, it is a blank, in this case the blank here will be an empty filter paper. You are taking a filter paper out of a box, it is not exposed to air, you keep it, it will show some reading. Yeah. You take it out, after some time switch on the balance again, put it again, it will show some reading. You do it 7 times. Non-consecutive times means the instrument may not give you the same reading each time. That is the other reason why we are doing it. This is also the fluctuation of the instrument. So, it is a noise that is generated by the instrument for various reasons. The reasons could be all kind of things, voltage fluctuations or the instrument is not working properly, anything. So, this is the sigma is the standard deviation of 7 non-consecutive measurements of a blank. What this means is that when you do 7 non-consecutive measurement, you are probably getting something like this. You will get 1 reading, 2nd reading, 3rd reading, 4th reading, 5th reading, 6th reading, 7th readings. You are getting a fluctuation. The standard deviation, this is the average approximately. The standard deviation is some measure of the spread. Now we are going 3 times above this spread. So, we are taking, if this is the spread, second, third. Only if you have a signal that is somewhere here, around here, we are taking that as the signal. This is significantly away from the noise. This is all the noise. These measurements are all the noise, and this we consider as the signal. Okay, clear? So, you have to measure the method detection limit for every instrument and every analyte. Whenever you set out to do an analysis method, the first information you need to know is the minimum detection limit, or this is method detection or minimum detection, all of them you can use both of these, minimum detection limit, but it is strictly speaking the method detection limit, because minimum does not mean anything. It is it's an undefined, it's a very vaguely defined term. Method detection limit is more specific. So, as we are going to be doing a lot of methods, each one of them will have a different detection limit. So, what is relevant to your measurement, that is all, okay. Because we are not going to be, sometimes we are going to be putting it on a filter paper, sometimes we will be putting it on something else, sometimes we may be doing various ways of doing it, and all of these have different ways of manifesting themselves in the instrument. So, the method detection limit or the based on this kind of analysis must be done, signal to noise ratio has to be done in order to do this. So, we have 2 things we have summarized here. If we go back to our original thing, we are now, the sample volume is based on the detection limit, the method detection limit of your measurement. Yeah, so how much volume you need to take depends on what is the instrument you are using, first of all. So, the instrument selection has to come up front at this point. The sample volume, so we will go back to, we will go to a new page. So, we will the factors determining, you have to choose the instrument, you have to select the instrument. Then you select sample volume, yeah. So, when we do different analytical methods, you will see the simple example we talked about, TSS applies there in all. The instrument we are using is not the gravimetry, it is not balance, but it will be other things, but the same thing applies for that also, okay. So, the sample volume is determined by these kinds of things. Instrument, you have to select the instrument first up front, which means you must know what are the instruments capable of doing it, okay. So, we come to the next question, we have about 5 minutes left, we will start this question. There is another term, some of you already mentioned it today's class, called as precision. What is precision? There is another term used in conjunction with this precision. So, when you take a measurement, there are 2 things people are always talking about. One is precision, the other one is accuracy. What is the difference between these 2, precision and accuracy? What is precision? What is precision? What is accuracy? We go to the easier answer. Accuracy. Yeah. Accuracy is closeness to what we call as true value. Is this an easy question to answer? What is the true value? Next question is, what is the true value? Why are we worried about this? This closeness to true value. This is, I think, the crux of all measurements is the value that you are giving. People are always asking, is it true or not? No. So then how will you prove it? You have to prove it. You have to prove that your value is as close as possible to, the reason I use the word as close as possible to true value is for the reason we discussed in the previous slide, is that you cannot get a single value. You are always going to get a range of values based on the what of the instrument? Precision of the instrument. So, the instrument will not give you the same reading every time you go, it will give you a range of values. So, every time you open a balance, you keep, it will give you one value, you keep open and keep it again, it will give you another value. Ideally 0, precision should be very good, it is the same, but the precision is not, instrument not very precise, and it will give you a range of values for various reasons. Okay. It relates to the instrument, the way instrument works. Okay. So, the precision is what we call as repeatability of a sample. For example, if I am taking a water sample, I measure TSS, I do once, I do it again, what is the value I get? Maybe different. Third time I do, I get for different value. So, I make TSS measurements, I send 3 of you to make TSS measurements, right. One of you gets a measurement of 105 milligrams per liter, the other one gets 108 milligrams per liter, the other one gets 103 milligrams per liter. What is the meaning of this? Somebody is all reporting 3 different values from, this is not an easy question to answer. This is where I think you have to take the entire system into account. I have a lake, all of you are taking samples from that, lake is a big sample, let us take well, let us say a well, I have a well, you go dip, put a bucket down, get some water, or put a pump, get some water. First sample 105, second sample 108, third sample 103. What does it mean? Is something wrong with the instrument? You do not know. What could be wrong? What could be the reason for this kind of measurements? They are different samples. What does it mean, different samples? You are right. Yeah? What does it mean when different samples? What do you mean by different samples? You are saying, well, I am taking water from. So, there is another piece of information that is missing.
Maybe location or time scale.
Time scale. So, how far is the time and location, both are important. Okay. So, I chose a well because well is small. If I say a river, river definitely it's moving. If I take sample every 5 minutes, I am not sampling the same thing, I am sampling something which is coming from upstream, I do not know what happened upstream, somebody just threw a bucket of mud in that 5 minutes between the 2 samples, so one of them is larger than the other, all these are possible.
It is not 100% uniform.
It is not uniform, so spatial variability is there for some reason. You have only partial information here, you only have this thing. Third reason could be, what could be a third reason? You have spatial non-uniformity, this is one, because of some time based event happening, something is happening in the time scale you are taking samples. Suppose I take 3 samples simultaneously, 3 of you are standing there, all 3 of you dip your sampler into it and take it at the same time, there is no time based event, it just represents spatial this thing. It could represent spatial non-uniformity, or it could represent that the instrument, the method you are doing, the instrument itself is like that, it does not measure, there is this much of fluctuation always there. How can you check if that fluctuation is really from the instrument or from the sample? This is a matter of precision, of repeatability of a particular sample. So, how do you establish that this is not coming from the system and it is coming from the analytical instrument? Now, how do you get the same sample? This is ostensibly the same sample, right, but you are not sure. By taking from the well, I am not sure that it is the same sample, we have all the reasons you have mentioned. So, what do you do now? No, we do not need a blank, we need a sample, we need something in the analyte.
Takes more volume and divide it into 2.
So, that is where this comes into question, this accuracy.